Let's start today's session. So we are discussing that Carnot cycle, and we saw that uh, Carnot gave a cycle in which four strokes we have to follow, four different types of processes in order to convert heat into work. And if we follow that four different types of processes, the cycle, in order to convert heat into work, we will get maximum efficiency. That is what is the main objective, because ultimately we are interested in achieving the maximum output. Now we will try to analyze it mathematically, like how is it possible? How the Carnot cycle can help us in achieving the maximum output. So for that, first we should be aware of the concept of efficiency, like how to calculate that, what is the mathematics behind that efficiency. That is what we will be discussing now. So we are calling it like the thermal efficiency. The thermal efficiency. We represent it with this sign. So thermal efficiency of a heat engine. And the Carnot cycle, it is for a heat engine, because heat engine, it converts heat into work. So the thermal efficiency of a heat engine. Any heat engine, if I have, how to calculate this efficiency? That is what we are discussing. The formula is something like this. Thermal efficiency is equal to work performed. Work performed is the output. Because what is efficiency? Efficiency is output upon input. So the output is work, and input is a heat energy. Output is the work. Input is the heat energy. Heat absorbed. Because we know that heat engine, uh, it absorbs the heat and performs the work. So this ratio gives us the efficiency. I can write it capital W upon QH. So QH is the heat absorbed, capital W is the work performed by the heat engine. And thermodynamically, I can write it, I can go one step ahead and write it like this. It is 1 minus QC by QH. Which is 1 minus QC by QH. So this was about thermal efficiency of a heat engine. Now, how the thermal efficiency of a heat engine will maximize if we follow the Carnot cycle, that we will look at it very soon. Before that, let us try to discuss the second law in terms of efficiency. Like two important statements we have to discuss of the second law of thermodynamics in relation with the thermal efficiency. Second law of thermodynamics. Let us see some statements. And this is known as, like, see, second law we have already discussed. Now we are focusing on the engine statement. Engine statement means these laws, these statements, we are mainly focusing on heat engine. So the engine statement we are discussing. Now what it is, let us look at one by one. The first statement, it talks about it is impossible it is impossible for any system to have an efficiency of 100%. So second law of thermodynamics states that it is impossible for any system to have an to have efficiency of 100%. Let me write it properly. To have efficiency, next time, bold and emphasize on this efficiency of 100%. And when the efficiency is 100%, we will write it like this. You will become, it is impossible according to the second law of thermodynamics. It means that, see, what is efficiency of 100%? Whatever heat we are absorbing, all of that we are converting it into the work, and that is not possible. It means that during the conversion process, like whenever we are utilizing the heat, some heat always it gets wasted, we lose it to the surrounding. So this is what the second law says that. And one more statement, very important statement. It is impossible for any process. It is impossible for any process to have as its sole result the transfer of heat. I will emphasize this. The transfer of heat from a cooler object to a warmer object. Transfer of from a cooler object. To a warmer object. It is not possible. And this is what we see around us, the world around us. Heat always flows from hot object to cold object. Body at a high temperature to body at a low temperature. Heat always flows in that direction. Heat never flows from cool object to warm object. And second law of thermodynamics, it proves that it is impossible for any process to spontaneously, naturally, see, like under some external conditions, we can make it happen. We can make it happen under some external conditions, but naturally, spontaneously, it will never happen. Like heat will never transfer from cool object to warm object. So this is the engine statement of second law, like the second law of thermodynamics in the context of heat engine or the engine state. So these are like very important discussion we made. Now we will get back to the strokes which we discussed, and we will try to analyze what is so special with this Carnot cycle that we can achieve a good efficiency. Why is it so? So as we have already seen that in the Carnot cycle, 4 strokes will be there. So in the first stroke, that is the curve AB, as we can see, the focus will be like the curve AB. The process is an isothermal expansion because we can see volume is increasing along the curve AB, and the curve is the isothermal. So isothermal expansion at any TH temperature, because isothermal means temperature constant, and let us suppose that constant temperature is TH itself, and in the expansion work is done always by the gas. Okay. Now what will be the idea? Let us look at it. Now the idea is that in this particular discussion, how the process will undergo, let us have a look into it. There is a heat source. We are calling it QH. I have a heat source QH. I will write simple. Just a minute. So I have a QH. QH is the heat source. Because ultimately in the heat engine, we need heat. So this heat, the gas comes in contact with this heat source, and this heat source is kept at a constant temperature, TH. So isothermal expansion at TH under heat source QH. I will take this QH there. And definitely when the gas will come in contact with this heat source, which is kept under a constant temperature, the gas particles, they will gain energy, their kinetic energy will increase, and they will start expanding. And hence isothermal expansion will take place. Now in this process, the entropy change. In this process, the entropy change, that is the delta S. I will write it. Change in entropy will be Q by T. So here it will be QH by T. QH by TH, where QH is the heat supplied by the source or the heat absorbed by the gas particles. And one more very interesting relation we can get from here. And what will be the work done by the gas? Work done by the gas. This work done by the gas, I will bring it up. Because now I will write the mathematical formula. This I will bring it. Work done by the gas. We will derive it. Let me call it the W. Now it is very clear to us that whatever is the heat absorbed, the work is done by the gas, so minus sign will be there. And what will be the work done? Whatever the heat will be absorbed, that should be the work done in the ideal scenario. And I know in an isothermal expansion, the work done, the formula we have derived it, that I'm writing it. Earlier we have derived it. It is RT log VB by VA. So it will be RT log or RTH, I will to be more precise. TH is the constant temperature. And since expansion is taking place, VB is the final volume, VA is the initial volume. So this is clear to us. First stroke. Now similarly, we will mathematically analyze the second stroke. In the second stroke, we have seen that the curve is the BC and adiabatic process will be there. Adiabatic means no heat transfer will be there. Heat will be constant. Expansion is taking place because volume is increasing, and whenever expansion is taking place, work is done by the gas. Now this work done is what we will calculate mathematically. So I will bring it. Since it's an adiabatic expansion, how we will achieve it? We will isolate the gas from the heat source. The connection of the gas particles from the heat source, we break it. Because of that, no heat transfer will take place. Whatever heat the gas particles have absorbed previously, the heat content will be same because the connection is broken, and hence we will be able to achieve an adiabatic process. We break the connection with the heat source. That is the idea. And because of that, since the gas particles still they have heat energy, their kinetic energy is very high, they will still undergo expansion. But here the expansion will be small. As can be seen in the graph, this expansion is relatively large. Here the expansion will not be very large because they are not getting a constant supply of heat energy in this BC process, like the cycle curve BC. This is clear to us. And since no heat transfer is there, so delta S has to be 0. Delta S has to be 0 because what is delta S? Change in entropy is heat upon temperature. Since it's an adiabatic process, no heat transfer will take place. So no change in entropy will take place. It means whatever is the entropy previously in the second cycle, second process, second stroke, in the second stroke, entropy will remain as it is. No change in entropy will be C. This is clear.
Yes.
And yeah, and here the temperature will fall. Why temperature will fall? Because heat content we are not getting, and heat is getting converted into work. So temperature will start falling. So, so two notations we are using. TH is the temperature of the hot source. TC is the temperature of the cold region. So in this scenario, work done by the gas will be, in this scenario, in this adiabatic expansion, the work done by the gas will be negative, and I will call it W2. Negative work done, W2, and it will be equal to minus CV, TH minus TC. So till there is a temperature difference between the hot source and cold source, like a hot region and cold region, until there is a temperature difference, work done will be carried out naturally, spontaneously. The work done will be carried out, and this is the what the work done will be. Now we will look at the third stroke. In the third stroke, we will be doing isothermal compression. So definitely isothermal, you know it, constant temperature. Now the temperature is kept Tc. So that now the temperature of the gas particles will be maintained at Tc. And work is done in the compression, work is done on the gas. So work done will be positive. Now here what happens is that the, the gas now it is placed in contact with the cold sink. In the third stroke, the gas is placed in contact with the cold sink, and hence it undergo compression. Because what happens when the gas particle is placed in contact with the cold sink, the gas particles, their energy, it will be sucked by the cold sink, and hence the particles, they will lose kinetic energy and they will come near. They will come close to each other, and hence a compression will be taking place in the third stroke. And this will keep on taking place. Yeah, and energy is released to the cold sink, that we have already seen, and there will be a change in entropy, and change in entropy we can write it mathematically, that will be delta S is equals to QC. Here QC is the energy sucked by the cold sink upon TC, that is the temperature of the cold sink. Or you can say that QC is the energy lost by the gas particles. And since QC is the energy lost by the gas particles to the cold sink, it will be negative. Loss of energy is negative, gaining of heat energy is always positive. So this is very good. And work done, we can calculate. So whatever is the energy lost, that much compression will be done. Whatever is the energy lost, that much compression will be carried out. So minus QC is the energy which is lost. Minus here, it is representing loss of energy. It will be equal to the work done. And we have already seen earlier that in isothermal compression, the work done is RTC log VB by VA. Now it will be VD by VC, because the final volume for the third stroke will be Vd, and the initial volume will be this. So this was third stroke. And finally the fourth stroke. In the fourth stroke, we have an adiabatic compression. And since adiabatic compression is there, no heat transfer will take place. It means that we break the connection of the gas particles from the cold source, cold sink. We break it. And because of that, uh, whatever uh, the energy is lost, whatever cooling has been taken place, that will persist. No further sucking of heat will be taking place. And particles will further compress. But now the compression will be relatively less. And because no heat transfer will be taking place, entropy, change in entropy will be zero. That is understood. So in this fourth stroke, delta S will be zero. Changing. And work done. Since compression is there, work is done on the gas. And work done on the gas that I can take. And work will be done till there is a temperature difference. It will be the same. Since work is done on the gas, it is positive. It is positive. Cv Th minus Tc. So this is the, like, mathematically we have analyzed, or like using thermodynamics, we have analyzed the Carnot engine, or the four strokes of the Carnot cycle. So in the first stroke, I can just mention it. Just one more point I have to share. Let us the first stroke, gas is in contact with the heat source. And I can call that heat source as QH. In the second stroke, the contact is broken. The second stroke, the contact is broken. Contact with QH, which is the heat source, is broken. In the third stroke, uh, gas is in contact with heat sink, QC. Gas is in contact with QC. And in the fourth stroke, the contact with QC is broken. And this is how that engine works. Carnot engine works in four strokes. Contact with QC is broken. So this is the idea. Now we will discuss it further. This graph. Let me copy. Bring some. Let me bring it here. Let us bring the let us. This is our graph. Now the area enclosed within the cycle, or the area enclosed by the four curves, it represents the net work done by the engine in one cycle. So let me shade that area I'm talking about. So I am talking about this area. This area which we have, it is the net work done uh, by the engine in one cycle. So this is the idea. Now we can do one more mathematical analysis. Total change in entropy around the cycle. If we try to understand that, total change in entropy around the cycle. It will be equal to sum of individual change in entropies. Sum of the changes in each of 4 steps. And I can write it like this. Total change in entropy over the cycle, it is equal to QH by QH by TH plus QC by TC. Because in adiabatic processes, change in entropy is zero. Only in the isothermal processes, there is a change in entropy. And in AB, the first stroke and the third stroke, there is a change in entropy. In the first stroke, the change in entropy we have already seen. Heat is supplied by the source to the gas particles. So QH by TH. And in the third stroke, heat is sucked by the sink from the gas particles. So QC by TC by TC, where TC is the temperature of the sink. So this is the total change in entropy for one cycle. And very interesting thing we will discuss. Experimentally, it has been seen that for an ideal gas, for an ideal gas, experimentally it has been seen that for an ideal gas, this change in entropy, like the sum total change in entropy around the cycle, it is zero. Total change in entropy around the cycle is zero. It is zero. It means that I can write QH, like for an ideal gas, QH by TH is equal to minus QC by TC.
अच्छा ओके
Because they're zero. Their sum is zero, so I can write it like this. Or I can take Q terms together and T terms together. QH by QC is equal to TH by TC. So this is for minus will be minus. This is for ideal gas. Now for an ideal, okay. So efficiency of a heat engine, we have already calculated it. Like calculated in the sense that mathematically we have analyzed it. Thermal efficiency of a heat engine. This formula just I copied. I can write it. Efficiency. What is efficiency? Output upon input. That is work done upon heat supply. And heat is supplied by the source. So QH. QH is the heat supplied by the source. QC is the amount of heat lost to the sink or the heat sucked by the sink. Bring it a bit closer. Okay. So this is the so less. And the statements which we did, we can name it also. Actually, a name is given to the statements. The first statement which we have discussed, the name given to this statement is the Kelvin's statement. We can do it. Kelvin's statement. And the second statement which we discussed, that is Clausius statement. The Clausius statement.
You have to learn the name.
Yeah, so it's my responsibility to like to tell you everything which is relevant. No, it's your call. Like, see, more precise you will be, the better you will impress the examiner. Because what is test? Test is understanding your knowledge. that they are testing your knowledge, how much you know. So the more you demonstrate, see, I know this also, this also, this also, then it will be good. And whatever is relevant, that I will discuss. Okay. Okay, so now we can look at the applications of Carnot cycle, and this applications of Carnot cycle is like something very important. Applications of Carnot cycle. Carnot cycle has some very good industrial applications also, like in the refrigerator, we call it like refrigeration. In the industries also, it is very important. Most of the chemical processes, they take place at extremely low temperatures. So therein we have to have some system for that. So it plays a role. So let us look at some important points in this context. The first point is energy efficiency. If I talk about energy efficiency, energy efficiency of the Carnot cycle is independent of its working substance. And this is a very important property offered by the Carnot principle or Carnot cycle. Is independent of its working substance. Like in the Carnot cycle, whatever formula we derived for efficiency, there nothing was mentioned about the material used, its conductivity or its thermal that heat capacity and all that. Efficiency depends only on the heat and the temperature. Like this, efficiency depends only on the either the heat or the temperature. It is independent of the heat capacity, because heat capacity is something which depends on the material or the working substance which is used, the gas, because different gas will have different heat capacity. So it's very interesting that Carnot cycle is independent of the efficiency of the energy efficiency of the Carnot cycle. It is independent of the working substance. It means that whatever gas we want to use, we can use it. And it is so interesting that we will be using that gas which is easily available to us. so that we can make cost effective solutions. So this is the one very interesting property we saw about the Carnot cycle. Second property, let us look at it. Second property is any cyclic process that absorbs heat at one temperature and rejects heat at another temperature and is reversible process has the energy efficiency of a Carnot cycle. We will understand this very soon. So first let me write it what this statement is. So any cyclic process that absorbs heat at one temperature and rejects heat at another temperature. And is reversible and is reversible as the energy efficiency of a Carnot cycle. Energy of the energy efficiency of a Carnot cycle. Of a Carnot cycle. This is also clear to us, like we can understand this. So the idea is very simple. We have already seen that in the Carnot cycle, we have a source and we have a sink. We have a source, we have a sink. Source is always maintained at a very high temperature. Sink is maintained at a very low temperature. Sink is maintained at extremely low temperature and The temperature of source and sink, they never fluctuate. It is maintained constant, and hence the process will be isothermal because temperature is kept constant. And QH is involved. QH is the heat of the source. QC is the heat of the heat sucked by the sink, and QH is the heat supplied by the source. Now, let us suppose I am not following the four-stroke thing. I am just performing an experiment wherein I am maintaining a source and a sink at constant temperature. Then what I will do is that I will follow a cyclic process in which I will go from here to here. Meaning to say that, let me be precise. Let us understand what we discuss. Just bring it close. Yeah. Now we will perform an experiment wherein in the first step I will supply heat to the gas. So when I will supply heat to the gas at point A, I will supply heat to the gas. For some time. And how I will supply heat to the gas? Open connection of the source. Open connection of the source. Open connection to source for 5 minutes, for example. For 5 minutes. After 5 minutes, what I will do? I will close the connection to the source and open the connection to the sink. After 5 minutes. After 5 minutes. Close connection to source. Close connection to source. Open connection to sink. Like I am just making a random process. Open connection to sink for next 5 minutes. And this random process, this pattern, I will keep on repeating every 5 minutes. So it will become a cyclic process. I have a cyclic process wherein for the first 5 minutes, the gas which I have, it will heat because when I open the connection to the source and here I have to close the connection also. So open connection to source and close connection to sink. Both I have to do. Close connection to sink. Close connection to sink. So what will happen is that In the process A, for 5 minutes, gas will heat. It will absorb heat energy. Yes, connection. In next 5 minutes, it will cool. It will lose its energy to the sink. Every 5 minutes, alternating 5 minutes, both the processes are taking place. Absorption of heat and rejection of heat. And it will keep on doing every five cycling. And if I calculate the efficiency of this process, it will be equivalent to Carnot cycle. And Carnot cycle is the efficiency which we appreciate, which is like an industry standard. Because Carnot cycle, uh, like very high efficiency. So now we got a secret recipe of thermodynamic systems, like all the thermodynamic system which we see, either the air conditioning system or the refrigeration system, wherein heat energy in motion is involved. To derive maximum work, we have to design a process wherein we are absorbing the heat and rejecting the heat, and we are doing it in a cyclic manner. And here itself, we designed one process, one random process we designed, wherein if we follow this A and B after 5 minutes in a reversible manner, we will achieve a very good efficiency. So this is the idea. Okay. Now let us look at some more applications of Carnot cycle. So we use so many thermal devices thermal devices or thermal machines. Like we have the heat pumps, the heat pumps to produce heating. Like they blow out hot air. The heat pumps to produce heating. Then we have the refrigerators to produce cooling. We also have the steam turbines used in the ships. We have combustion engines, like engines in the automobile, the burning of the fuel, that is the combustion engine. Wherever the burning of the fuel is there, that is the combustion engines. The combustion engines of the combustion vehicles. So in all these processes, like in all these systems, uh, the Carnot principle is used. Combustion vehicles. Carnot principle of alternating uh, heating and cooling of gases or the working substance. Working substance can be liquid also. The reaction turbines of the aircraft. Now, one last thing we have to emphasize on, then we are done. Like now, we will be focusing on the refrigerator, the refrigeration, air conditioners, and heat pump systems. How they work last for this Carnot cycle. Refrigeration, refrigeration, air conditioners, and heat pumps. Let us see how. So I will just make one demonstration picture. Okay. So ideally we have some strips in the refrigerator in the back, and this is there in air conditioning system also. But in the back, the refrigerator it is so easily visible. Every fridge you take, see inside outside the, like, at its back, there is something like this. Strips out there. Just making a rough type. Our goal is to just understand the purpose of it and how the cooling is taking place from the perspective of thermodynamics, the subject which we are studying, so that we can appreciate its applications, appreciate the application of the principles of thermodynamics in the real world. Let me try. Just a minute. I will select, I will copy it and paste it. That is what I want to do. Now I will bring it back. Okay. Yeah. Okay, now let me give it fast. Now I am drawing a pipe. Okay, pipe. This pipe we can see in the rear part of the fridge. What it is and the principle that we will discuss. Here we have a valve. Here we have a valve is kind of a connector. Like we can connect two pipes using this valve. This valve is connected to one more pipe that I will draw somewhere here. Pipe will be connected. So this is the blue pipe. So when I have blue pipe, I have a brown pipe. I can say that. Let me start naming important components. This is the red valve. Expansion valve. This is the expansion valve, and the brown pipe, it is the high pressure. High pressure. And the blue pipe, it is the low pressure. Like low pressure is maintained in the blue pipe, and this pressure is maintained via some external device which we will discuss, like the compressor. Compressor is used both in fridge also and the AC also. So the compressor, that what is the purpose of that? It maintains the pressure difference. So in one of the region, like in the brown pipe, high pressure is maintained. In the blue pipe, low pressure is maintained. Now, what is the purpose of that? Let us try to understand, like, why we are maintaining the pressure difference, high pressure, low pressure, what benefit we will get. Let us try to understand. So, the high pressure which we are maintaining, because of that, what we are trying to achieve is that we are releasing the heat to the surrounding. So QH outside. So the rear, the back part of the refrigerator where we can see something like this, the objective of that is to radiate heat outside. And this blue pipe, it is there inside the fridge. It is there inside the fridge. And what is its purpose? To suck heat from inside the fridge. And when I suck heat from inside the fridge will become cool, and that is what I want. Fridge will become cool, that is what I want. So this blue pipe, its purpose is to suck heat from inside the fridge. And suck heat from inside. Now, what benefit I will get is what benefit I will get is this blue pipe. It it will suck heat, so the particles in it, they are already in low pressure. Because of the low pressure, they are in a position to absorb the heat, and hence they can increase their kinetic energy because they have the space to move, to expand. If pressure is high, expansion will be difficult. So low pressure is maintained, because of which the particles, they can easily absorb the heat, they can expand, and they come in contact with the brown pipe. And when they will, when this energetic particles, which has sucked heat, which has become hot, they get inside the brown pipe, there is pressure is very high, high pressure. There is no scope for further expansion. And ultimately, because of the high pressure, they will start compressing. And when they will compress, they will release the heat, and heat energy will be released outside. So sucking is taking place and releasing is taking place. And this is a reversible process. It will keep on taking place. And that is what is Carnot principle is saying. Uh, like these two alternating processes should be reversible, and hence the fridge we use, or in AC also similar thing is happening. In the AC, the cool air which has been blown out, first the heat is sucked from that region, and the air becomes cool, and then it is blown out, it is given out. So the same principle is used in the air conditioning system also, in the refrigerator system also. In the heat pump, opposite will be done. In the heat pump, opposite process will be done. Now, in order to maintain this pressure difference, some device will be employed, and that we call it like the compressor. And that compressor needs electricity to work. It cannot work on its own. It needs electricity to maintain the pressure difference. To maintain the pressure difference. So here I have a compressor. I'm just making a rough diagram of it. So the purpose of the compressor is to maintain the pressure difference. And this pressure difference helps us to suck and to release. Both the pipes, they are connected with this compressor, so that a relevant pressure difference can be maintained. And this is the principle. This blue pipe, it is called as cooling pipe. In the terminology, the blue pipe, it is called as cooling pipe, and it is present inside the fridge that we have already seen. Just cooling pipe. Let me write this. Yeah, it's working. Cooling pipe. And this brown pipe, it is called as condenser pipe. Condenser. And very interesting thing is that when the gas particles they travel this pipe and reaches the compressor, because compressor will try to suck the air, it vaporizes. So we get two interesting things. So this brown pipe just near the compressor, it will be having high pressure vapors. It will be having high pressure vapors. And the blue pipe just near the compressor, it will be having low pressure vapors. So this is the mechanism of refrigeration. Now, now I don't need this because we have understood that in one diagram itself. No need to draw it separately. Now we can just draw a simplified version of it because now concept is very clear to us. Two components are involved, QL and QH. What is the role of QL? QL sucks the energy, heat energy from the interior, and QH radiates that energy to the outside world, like to the surrounding. So QL sucks the heat energy from the system. QH is the heat energy which is being thrown out to the surrounding. This is the idea. And this process is not spontaneous. If it would have been spontaneous, then the refrigerator AC, it would have worked without electricity. It would be so good. But unfortunately, this does not happen. We have to do external work in order to achieve this. And that external work we do using a compressor. Compressor will be doing that work. And compressor will be connected to a electric source. And I can write it something like this. Just very quickly I will. And then this will be completed. I have two regions. Let us suppose this is the region of high temperature, and let us suppose this be the region of low temperature. This is pH, high temperature. This is TL, low temperature. And as we have already seen, heat energy is sucked. This is the interior from the system, and it is been carried forward through these special pipes to the surrounding. And this sucking and throwing out the energy, it needs a work. Work needs to be done. And this is how the system works.
Yes.
So this is the core idea of this. Just one point we will write, then this is complete. Now, okay, so like I will write it here. It's understood. But you can emphasize it. I'm just writing it. Work is done. External work is done. Work is done. To extract heat from cold reservoir, because this TL, the system, it is relatively cold, and spontaneously heat can never flow from cold to hot, but it is flowing because of the external work. So work is done to extract heat from cold reservoir. This is a system which is the interior of the fridge. This is the interior of the fridge. And exhausted to the outside surrounding, to the hot reservoir, which is the surrounding. And exhausted to the hot reservoir. So this is all about Carnot. cycle.
Yes, sir.
I have entered the string.